Yes. All right. All right, let's get started, folks. We're going to talk about sequences and series today. Well, the first thing we need to know is when we talk about a sequence, what are we talking about? We talk about a sequence of something. What?
Numbers.
It could be a number, but just in general. If we talk about a sequence of events, what do we mean?
Numbers. Like 2, 4, 6.
I don't know the word for it, but like
And even not even thinking of numbers, just what's a sequence? Something in order. That's what we're looking for. Something in order. Something in some kind of order. Did I start this? Yes. All right. So for math, in math, a sequence is going to be basically a list of numbers. And our numbers, these numbers are going to have some kind of relationship to each other somehow. So they're going to be in some kind of order. When you go further in Calc 2, you'll study sequences and series in quite a bit more detail, and you'll go into more detail about how the things are arranged. But for now, we're talking about a list of numbers. Each number is a term. So we have this list of numbers. We call each number a term of the sequence. So, and for sequences, we usually use a subscript notation. A sub n is one term. And this n tells us which term. So, for example, a sub 1 is the first term. A sub 2 is the second term, etc. So that tells us where we are in our list of numbers. If we put braces around our a sub n, brackets are square, braces are curvy like this. A bracket, this would be a bracket. These are braces. This refers to the entire sequence. They just have to be little squiggles. Little squiggles. So when we put the braces around this is the entire sequence. So if our sequence is 100 numbers, we can refer to all 100 numbers at once by writing braces a sub n. So for example, a sequence could be 1, 1, 2, 3, 5, 8, 13, ... Anybody know what this sequence is? Yeah? This is the Fibonacci sequence. It has to do with spirals. They talked about this indirectly. They talked about it in Donald in Math Magic Land. That was fun.
Watch it on your own time. It's so great.
And in this sequence, a sub 1 is 1, a sub 2 is 1, a sub 3 is 2, etc. All right, so let's look at a couple of examples. For all of these examples, we want to list the first four terms. What's that? That was just a Fibonacci sequence.
Is that all we wrote for it?
Yep. Just as, yeah.
Oh, like an example for the sequences?
Yeah. List the first four terms of, here this sequence a sub n is given by 2n plus 5. So we have a nice formula for this, for the nth term, what we call the nth term. So a sub 1 is 2 times 1 plus 5. So that would be, 1 plus 5, 7. A sub 2, 2 times 2 plus 5, which is 9. A sub 3, 2 times 3 plus 5, which is 11. And a sub 4, 2 times 4 plus 5, which is 13. So we just plug in our n, and we get our term. Let's look at b sub n. B sub n is 3 to the n minus 1. So b sub 1, 3 to the 1 minus 1. So 3 to the 0, which is 1. Anything to the 0 power is 1. B sub 2, 3 to the 2 minus 1 is 3. B sub 3, 3 to the 3 minus 1, which is 9. B sub 4, 3 to the 4 minus 1, which is 27. So we get our powers of 3. C sub n, negative 1 to the n over n squared plus 1. What is that negative 1 to the n going to do to our terms? What's that? They're going to switch between negative and positive, right? Because odd powers, negative 1 to an odd power is going to be negative. Negative 1 to an even power is going to be positive. So C sub 1 is negative 1 to the 1 over 1 squared plus 1, which is negative 1/2. C sub 2, negative 1 squared over 2 squared plus 1, which is positive 1/5. C sub 3, negative 1 to the 3rd over 3 squared plus 1. Negative 1 to the 3rd is going to be negative 1, and we get a 10 in the denominator. And C sub 4 is negative 1 to the 4th over 4 squared plus 1. We have an even power, so that's going to be positive 1/17. So we get our signs alternating, minus, plus, minus, plus. When we have a formula like this for the nth term, where we can just plug in n and get our number, we call these explicit sequences. So for an explicit sequence or an explicitly defined sequence, we have a formula. We just plug in n and we get our term. There are other kinds of sequences, other ways of getting the terms of a sequence. So we can also have what we call, are we good with these examples? We also have what we call recursive sequences. And a recursive sequence is one where we need previous terms to get new terms. So for our explicit sequences, we just plug it in and we get our number. Here we need to know previous terms. So for example, I could say a sub 1 is 5. And a sub n equals a sub n minus 1, the previous term, and I want to multiply that by 3, plus 2. So 3 times the previous term plus 2. And this is going to be for n greater than or equal to 2. So we know one term, and this tells us how to get the next term from the previous term. So a sub 2 is 3 times a sub 1 plus 2, which is 17. A sub 3 is 3 times a sub 2, 17, plus 2. So we get 53. And a sub 4 is 3 times 53 plus 2 is 161. So our terms are 5, 17, 53, 161. Yeah.
Why is there 39 in the a sub n?
Oh, no, this is 3 times a sub n minus 1. So for the Fibonacci sequence, we could say a sub 1 is 1, a sub 2 is 1, and a sub n is a sub n minus 2 plus a sub n minus 1. So for the Fibonacci sequence, we need 2 previous terms to get the next term. There are other ways to define the Fibonacci sequence, but this is one way. There is an explicit formula for the Fibonacci, the terms of the Fibonacci sequence, but it's pretty complicated. And often, we can find a recursive definition for a sequence and an explicit definition for the sequence. Usually an explicit definition is going to be easier to work with. All right, questions so far? All right, so one thing that comes up often in sequences and series, and we'll also use it again when we talk about counting and probability, is factorial notation. Factorial notation is n factorial. This, I think this is the funnest, most fun symbol, one of the most fun symbols in math. This doesn't necessarily mean we're really excited about n, but it can mean that. And this n factorial is 1 times 2 times 3 times dot dot dot, all the way up to n minus 1 times n. All the numbers that are less than or equal to n multiplied together. So for example, 5 factorial is 1 times 2 times 3 times 4 times 5. The number, 1 less, 2 less, 3 less, all the way down to 1. And this is 120. There's one special case for factorials. 0 factorial is 1. And it needs to be that way for things to work out properly. And there are also arguments that you can make that 0 factorial is 1. In terms of order of operation, 2n factorial Factorial has the same place in the order of operations as exponents. So they're the same place in PEMDAS as exponents. You do factorials first. So 2n factorial is 2 times n factorial, which is 2 times 1 times 2 times 3 times dot 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 to the all the way to n. In contrast, 2n factorial is 1 times 2 times 3 times dot dot dot, and we're multiplying all the numbers up to 2n, including 2n. So 1 less than 2n is 2n minus 1 times 2n. So let's look at some factorials. We know that 0 factorial is 1. That's by definition. What is 1 factorial? 1. 1 times is just 1. 2 factorial. 2. 1 times 2 is 2. 3 factorial? 6. So that's 1 times 2 is 2 times 3 is 6. 4 factorial? 24. We would multiply this by 4. And we said 5 factorial was 120. 6 factorial is 720. Factorials grow very, very quickly. So let's look at a couple of examples using factorial notation. We want the first 4 terms of a sub n equals n squared over n factorial. Well, a sub 1 is 1 squared over 1 factorial, which is just 1. A sub 2 is 2 squared over 2 factorial, which is 4 over 2, which is 2. A sub 3 is 3 squared over 3 factorial, which is 9 over 6, which is 3 halves. And a sub 4 is 4 squared over 4 factorial, which is 16 over 24, which is 2/3. Those would be our first 4 terms. Questions there? All right, so something that we will often have to do with factorials, especially when we're talking about counting and probability, but it comes up in sequence series as well, is simplifying factorials. So let's simplify these things. 10 factorial over 2 factorial times 8 factorial. This a quantity like this will come up often when we're counting things. So what we're going to do to simplify this, I just write them out what they are. 1 times 2 times 3 dot 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 times 9 times 10. And I'm going to add one more times dot 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 times 8 times 9 times 10. And on in the denominator, 2 factorial is just 2 times 1 times 2 times 3 times dot 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 times 8. Well, what can I do with this quantity and this quantity? Then we're just multiplying, so we can just cancel those two out. That cancels with that. I can reduce 10 over 2. to 5 over 1. And this is just 9 times 5, which is 45. So factorials simplify nicely. In sequences and series, you may end up with a quantity. Let's make it a little more interesting. N factorial over n plus 1 factorial. Now, we cannot just cancel out the factorials. That's kind of like doing one of these things.
Can we actually do?
You cannot cancel out the factorials. But what we're going to do is write 1 times 2 times 3 times dot 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 all the way up to n. And in the denominator, we have 1 times 2 times 3 times dot 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 times n plus 1. Well, what can I do with this and this? I can cancel all those out. So this is just 1 over n plus 1. And let's make it one step more interesting. N plus 1 factorial over n minus 1 factorial. We can do the same thing. Just write it out. 1 times 2 times 3 dot dot dot. And I'm going to write this in a convenient way. Times n minus 1, because that's still less than n plus 1, times n, that's 1 bigger, and then I get to n plus 1. And in the denominator, I have 1 times 2 times 3 times dot dot dot, all the way up to n minus 1. And then I can cancel all of these. And this equals n times n plus 1. Yeah.
Do you want us to like distribute those?
You could, but this is fine. Yeah.
Is there any way to do it that faster than multiplying, or you just have to figure out what each quantity is?
Like, so if you were given,
Like, say that 2 times 8 is more complicated numbers than 2,
oh no, you can always do it like this.
but you have to like find out what is a 6 factorial.
Right, right. The other way that you can think about this is you can think of n plus 1 factorial as n minus 1 factorial times n times n plus 1. So this is 1 times 2 times 3 to the n all the way to n minus 1. And then we multiply by n plus 1 to get n plus 1 factorial over n minus 1 factorial. And then we can cancel those two out. So just a slightly different way of thinking about it. Yeah, you don't have to write all the 1, 2, 3, dot, dot, dot. So we could do the same thing here. We could have done the same thing here and written n plus 1 factorial as n plus 1 times n.
Where did you get that times n plus 1?
Because n plus 1 factorial is 1 times 2 times 3, dot, 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 all the way to n minus 1. That's this. If I just looked at that part, that's n minus 1 factorial.
But the n.
Where do you get the
The
n?
n, because we have to go to n plus 1. So n plus 1 factorial is 1 times 2 times 3 to n times n minus 1 times n plus 1.
You lost me. Okay, no, think about it with numbers.
Okay, this quantity here,
I'm thinking about what numbers this is.
that quantity there, 1 times 2 times 3 times n, all the way to n minus 1 is n minus 1 factorial. And then for n plus 1 factorial, then we have to multiply it by n times n plus 1 because we want to go all the way to n plus 1.
How does that factor out?
Oh no, it's just like it's just a sequence.
And this quantity is also n plus 1 factorial. Sorry, n minus 1 factorial. You don't have to think about it this way. You can always think about it this way.
No, that's the question is like where is the n by itself? Why do we need it?
Because, listen up. So if we want to get to, n plus 1, we want to multiply all the numbers n plus 1 times all the numbers that are less than n plus 1, right? Well, what's 1 less than n plus 1? N. What's 1 less than n? N minus 1. 1 less than n minus 1, n minus 2.
Understand that.
So if you think about, you can also think about it in reverse. Some people prefer to think about it in reverse, and instead of writing 1 times 2, they write n plus 1 and n minus 1, 3, 2, 1.
All right, that makes more sense.
So you can think about it in reverse as well. Okay. All right.
Homework.
Not yet.
Just kidding.
So we're not always given the formula. Sometimes we're just given a list of numbers. And we need to figure out a rule for the nth term. So that's what we want to do next. Um, 0, 3, 8, 15, ... So what we want to do here is come up with, this is n equals 1, n equals 2, n equals 3, n equals 4, some kind of relationship between the term number and the number that we have there. So we can write a formula that involves n. Anybody see what it is? Yes.
N squared minus 1.
Each of these is 1 less than a perfect square. 3 is 1 less than 4, 8 is 1 less than 9, 15 is 1 less than 16. So this is 1 squared minus 1. This is 2 squared minus 1. This is 3 squared minus 1. That's 4 squared minus 1. So this would be comma n squared minus 1. Now, there may be other ways that you could come up with a formula for this. That's the one that jumps out at me as well. How about 1/2, 1/6, 1/24, 1/120th, comma, ... What about those?
1 over n.
Yeah, 1 over n factorial.
Yeah, these are all factorials, right? 2 factorial, 3 factorial, 4 factorial. So this would be 1 over n plus 1 factorial. Because usually we want to start our n at 1. How about negative 2/3, positive 3/4, 4/5, negative 4/5, sorry, 5/6, negative 6/7. So because we have these alternating signs, what do we know for sure that we have to have? We have to have a negative 1 to the n, right? Exponent, we have a negative, we have to get our signs to alternate. And then, well, this is 2, 3, 4, 5, 6, 3, 4, 5, 6, 7. If this is n equals 1, n equals 2, What's that really?
And this top thing
N
plus 1.
plus 1 over n plus 1 over n plus 2. And that would get us that sequence. This and coming up with these terms is really about recognizing the patterns between the numbers. And the more that you do that, the better you get at it. All right, the last thing we need to talk about for today is what we're going to do is we'll have a sequence of numbers. We often are interested then in adding those numbers together. So we need to talk about summation notation. So our summation notation is, we write this nice symbol. This tells us to add. This symbol is a capital sigma. And here we call I is the index. One is the lower bound. And n is the upper bound. So what this is saying is the summation, the way we pronounce it, the sum I equals 1 to n, a sub I, is a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n. So we're just adding all of our terms. So for example, the sum for I equals 1 to 4 of 3 times I. This is just telling us to do 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4. This is our formula for a sub n. And this is telling us to add these 4 terms together. So this is 3 plus 6 plus 9 plus 12, which is 30. Yes?
So in this case, I is acting like n, not like the square root of negative.
Yes, here I is not the square root of negative 1. I is just some numbers. That's kind of like the student that came home and told his parents, my math teacher's crazy. Yesterday, the math teacher told me x was 10, and today they told me x is 3.
That sounds like something I would say.
Yeah.
Those Roman numerals.
Right. So sometimes in very specific situations, I is a square root of negative 1. Other times, I is just some number.
But you also written it.
I have. Usually,
A swishy one.
yeah, usually you do a swishy one for a square root of negative 1. A couple of properties of sums. Did you have a question, or were you just gesturing? Okay. If we have a sum of a term multiplied by a constant, we can factor that constant out. if we have two sums that are added or subtracted to each other, we can combine those together. This should be I, sorry. So we can combine those together into one sum. Yes. Then you would, for this to work, they have to be the same. Well, we give these sums a special name. We call this a series. So we call a sum a series. So a series is the terms of a sequence added together. If we add up an infinite number of terms, sorry, this should be I, we call it an infinite series. And an interesting thing happens with infinite series, because we can sometimes add up an infinite number of terms and get a finite number. If we have an infinite series and we only add some of the terms together, the sum I equals 1 to n a sub I is the nth partial sum. So if we add 10 terms together, we call that the 10th partial sum. If we add 20 terms together, we call that the 20th partial sum. If we add 36 terms together, we call it the 36th partial sum. Yes? I will eventually show you how to do it on your calculator.
After we know how to do it by hand.
Right. So let's take a look at an infinite series that adds to a finite number. All right, so there's our infinite series. Let's write some terms. Well, this is 1/10 plus 1 100th plus 1 1,000th plus 1 10,000th plus dot dot dot. Well, let's write these as decimals. 0.1 plus 0.01 plus 0.001 plus 0.0001 plus dot dot dot. Well, this is 0.1111 dot dot dot, which is 0.1 repeating. And we know that a repeating decimal can be written as a fraction. Does anybody know what the fraction? 1/9. So the sum from 1 to infinity of 1/10 to the I is 1/9. Yes?
How did you figure out it's 0.11?
Because this is, when I add 0.1 to 0.01, I get 0.11. When I add a 0.001, I get 0.111. I just keep adding a 1 at the end each time. So there's an infinite series that sums to a finite number. Interestingly, you can use this process to write any repeating decimal as a fraction. You can figure out the fraction for any repeating decimal using this process. It also shows us that two numbers, any number has two different representations. 1/9 is 0.1 repeating. Those two are the same thing. 1 is 0.999 repeating. They're equivalent representations of the same number. All right. And I hear people asking for homework. So I will oblige.
I think you should shorten the amount of questions.
I think you should just not give us questions. Give us one singular question. We do it.
All right. We are done. All right. I'll make the homework smaller. EO every other odd. EOE every other even. I said I'd make the homework smaller.
Oh, that's clever.
All right, there you go.